we're again looking at, we're going to look at dependent events. And again, we're looking at our Sick Kid Lotto. They gave us a whole bunch of info. Here are all our prizes, and we quickly added them all up. And because of the odds of the event, we assume this is our estimate of how many tickets they're selling. So it's 150,930 tickets being sold. So with that being said, let's talk about the idea of dependent events. Dependent events are usually written of the probability of A and B both happening are equal to the probability of event A times the probability of event B given that A has occurred. Okay, so this looks a little funny. That's like a line in between saying given that A has occurred. And in most lotteries where they're pulling tickets out of something, this is how they're run. They're dependent events. Okay, so let's talk about, we want to know the probability of you winning one of the vehicles. We'll call this probability A. Okay, and you win a wonderful vacation package. Ooh, okay. Oh, that's a B. So you win a wonderful vacation package on top. So you can drive to your vacation in a new vehicle. Okay. So these are going to be events A and B, let's say. Well, first we have to talk about what the probability of the event is happening. Well, because there's two prizes out of the total 150,930 tickets, it's a 2 out of this value for the probability of event A. Okay, so probability of A is equal to 2. You get 2 chances to win, and there's a total of this many tickets. Okay. Now, normally the probability of B would be identical. The probability of B, you have 2 vacation packages. Okay, so it would be a 2 out of 150,930. Okay, but what we're doing is we're assuming, okay, we're making the assumption that you already win the vehicle. And what that means in dependent events, like we said, here's our wonderful pot of tickets. And they go in and they pull your ticket. Yay! That ticket does not get replaced. It stays out. That way, that one ticket doesn't win every single prize. It could happen. The odds are ridiculously low in this type of lottery. But they don't replace it. So essentially, if you only buy one ticket, you can only win one prize, right? If the ticket was replaced, a person could buy one ticket and potentially win every single prize. Be a super lucky person. So because it's not being replaced, we now no longer are out of 150,930. Okay? Because one ticket was drawn, we have to subtract by that value. So we now have 150,929. Yes, very good. 150,929. So not much better odds. Still really, really rare. But the dependent events do change the odds. Okay? So this is given that A happens. That didn't really fit in there. So probability of B was the 2 in 150,930. But the probability of A given B is a little bit different. Sorry, of B given A has occurred. It's a little different. Our denominator is a little different. So, to calculate these two events, what do I have down there? Oh, sorry, that's from the other one. Where we set. Probability of the two events, so the probability of A and B occurring, that should be a B, of the two dependent events, are probability of A being 2 out of 150,930 times 2 out of 150,929. A little bit different. Okay, so it approximately equals 4 out of, and I can't write that squared like I did in independent events because these numbers aren't technically the same. So that times this when we multiply fractions. 929. So a ridiculous number. I don't even know if I'm going to write it down because the probability is going to be so very low. We're going to say 4 divided by, in brackets, and then we'll multiply these two values. So 150,930 times 150,929, end bracket. Okay, so it's 4 divided by these two numbers, multiplied. And again, so this negative 10 means that we move this decimal place 10 place values to the left. That means there are 9 zeros in front of that 1. the probability that you would win both of these are much closer to 0 than they are to a whole number percentage. Okay, super, super low. Let's just say, okay, now I want to talk about this idea of a dependent event. What if I say probability of A? I'm going to erase this here. We'll have a new thing. All right, we'll call it probability C. Let's say probability of C is, I don't know, winning the grand prize. Okay. So winning grand prize, there's only one grand prize, so it's a 1 in 150,930 chance. And the probability of D, okay, is winning a prize. Okay. Well, we know there's, and we're not going to count that 50-50 draw. We know there's 50,330, okay, 50,300 and, 10, not 30, out of 150,930. That's the probability of winning a prize, okay, that's a probability. But when you think about this idea, it's a little different. Probability of D given C. What is your probability that you win a prize if you've already won the VIP? It's a weird idea. What's the probability that I've won a prize, okay, that I win any prize, given that I've already won the VIP prize? Close. You're thinking in the right idea, okay? The idea that you've already won the prize.
Yeah.
So technically it's 1 in 1 or 100%. You've already actually won the prize. So it completely changed everything here, okay? Because this D wasn't the probability of winning a different type of prize. It was just winning any prize in general, okay? So that really changed this, where the order technically becomes important. I guess that's how we're going to leave it. We'll leave it as a simple idea. We could change them vice versa, and it gets a little more complex of probability of winning a prize, and then what's the probability that you won the VIP prize. Actually, we can quickly talk about it. So D given C. What if we did it in the other order? Probability of D given C. Well, if we haven't already won the prize, okay, sorry, not D given C. We're going to say probability of D to start. So probability of D is equal to that 50,000. So what's the probability we won a prize? Those are the number of prizes out of the number of tickets. And then the probability of C, given D. A little different here. What's the probability that we won the grand prize? Well, there's only one grand prize. And how many prizes were there in total? 50,000. So that probability is very, very different. That's 1 out of 50,310. Again, really different from before. Yeah. Okay? So we know we won a prize, but of the prizes, well, we're looking for that 1 out of the 50,000 plus prizes there were to win. And then again, we just multiply these two percentages. So when events are dependent, the way things are worded and in what order is really important. Like, this one here, it's 100%, so this is the probability. But here, it's a far less likely probability that if you've won a prize, that it's actually the grand prize. So the order of things becomes very important and kind of confusing when it becomes dependent.